Quotient groups. In this module, we introduce the notion of a quotient group of a group G, which is another way of obtaining a smaller group from group G, and as we did with subgroups, we shall use quotient groups to study the structure of the quotient groups and the subgroups of G. Let's start with the coset of a group G. Definition of a coset of H in G. Let G be a group and let H be a subgroup of G. For any A belonging to G, the set AH is equal to the set of all elements AH such that H belongs to H, and HA is equal to the set of all elements HA such that H belongs to H. They are the left coset and right coset respectively. By combining normal subgroup and cosets, we can define a quotient group. The definition is: let G be a group and let H be a normal subgroup of G. The set G bar H of left cosets under coset multiplication is the quotient group or factor group of G by H. The upcoming examples will give more clarification to you. Now we shall see some examples of quotient groups. Example 1, we know that the set of integers under addition is an abelian group. So 3z comma plus is a normal subgroup in Z. Now 0 plus 3z, the coset, is given by the set minus 6, minus 3, so on up to infinity, and 1 plus 3z is also from negative infinity to minus 5, minus 2, 1, 4, 7, 10, etc. 2 plus 3z is also given by negative infinity to minus 4, minus 1, 2, 5, 8, 11, etc. We can clearly see that there are only 3 distinct left cosets of 3z in Z, namely 0 plus 3z, 1 plus 3z and 2 plus 3z. Let's check whether there are any other cosets other than these 3 cosets. Let's check for minus 7 plus 3z. Clearly, we can see that it is the same as minus 10, minus 7, minus 4, minus 1, 2, 4, 7, etc. is similar to 1 plus 3z. Therefore, minus 7 plus 3z is the same as 1 plus 3z. In the factor group, any product A plus 3z times B plus 3z is one of the cosets in the group. So, we can see a table here. I have done the product of all the cosets that are possible here. We can clearly see that in this table that 0 plus 3z times 0 plus 3z is 0 plus 3z, 0 plus 3z times 1 plus 3z is 1 plus 3z, and so on. So, whatever product we do, we are getting that it is only 0, 1, 2, 0, 1, 2, etc. So, there are only 3 distinct cosets under the product of the factor group. Next, we shall see one more example. Example 2, the set of integers Z6 under addition is also an abelian group. So, clearly all the subgroups are normal. Let us take the subgroup H is equal to 0, 2, 4. It is a normal subgroup of Z6. We know that H is 0, 2, 4. So, 0 plus H, 2 plus H and 4 plus H are definitely H. So, the elements, let us calculate for 1 plus H. 1 plus H is equal to 1 plus 0, 1 plus 2, 1 plus 4. So, since Z6 is a cyclic group, 1 plus 0 is 1, 1 plus 2 is 3 and 1 plus 4 is 5. Likewise, for 3 plus H, it is 3 plus 0, 3 plus 2 and 3 plus 4. Since it is a cyclic group, again 3 plus 0 is 3, 3 plus 2 is 5 and 3 plus 4 is 1, 7 when divided by 6 is 1. Therefore, 3 plus 4 is 1. Now, 5 plus H is 5 plus 0, 5 plus 2, 5 plus 4. So, 5 plus 0 is 5, 5 plus 2 is 7, again it becomes 1 because Z6 is cyclic. Then 5 plus 4 is 9, but because it is when you divide by 6 you get the remainder as 3, therefore, it is 5, 1 and 3. So, clearly we can see that all of them are equal, 1, 3, 5, 3, 5, 1, 5, 1, 3, they are the same, therefore, they are equal, and only 2 distinct left cosets are possible. Now, let us consider the factor group Z6 bar H, then Z6 bar H is 0 plus H comma 1 plus H, that is the set 0, 2, 4 and the set 1, 3, 5. 0 plus H times 0 plus H is 0 plus H, which is again 0 plus H. 0 plus H times 1 plus H is 0 plus 1 plus H, so 0 plus 1 is 1. And likewise for 1 plus H times 0 plus H is also 1 plus H, and 1 plus H times 1 plus H is 2 plus H, but we know that 2 plus H is H, so that is equal to 0 plus H. Therefore, 0 plus H, 1 plus H, this is of the order 2, 1 plus H is of the order 2, and 0 plus H acts as the identity element, and therefore, this is a cyclic group generated by 1 plus H. Now, Z6 bar H is a finite cyclic group of order 2, and hence we can clearly see that Z6 bar H is isomorphic to Z2. Now, we shall see a theorem. Let G be a group and let H be a normal subgroup of G. The set G bar H is equal to the set of all elements AH such that A belongs to G. This is a group under the operation AH times BH is equal to ABH. Let us prove that this function phi from G bar H times G bar H going to G bar H is well defined. Let us assume that the elements A dash, B dash belong to G, and AH is equal to A dash H and BH is equal to B dash H. So, when you are doing the product of these two elements, AH times BH is equal to A dash H times B dash H, which is equal to ABH is equal to A dash B dash H. So, this statement implies this statement. So, we have just rearranged the terms here. So, ABH is equal to A dash B dash H. So, clearly it is a well defined operation, and therefore, we now have to show that the multiplication depends on the cosets and not the coset representatives. We shall show that G bar H is a group. Now, consider the elements A dash is equal to AH1, B dash is equal to BH2, where H1 and H2 belong to H. We know that AH is equal to A dash H and BH is equal to B dash H. Therefore, when you do the product of these two elements, A dash B dash H is equal to, on the right hand side we have AH1 BH1 times H. So, let us rearrange the terms. AH1 BH2 H becomes BH since AH is equal to AH, and therefore, that is equal to AH1 HB, that is equal to AHB, and that is equal to ABH. All this is possible because H is a normal subgroup of G. Now, for this group G bar H, clearly EH is equal to H is the identity element, A inverse H is the inverse of AH, and now we shall prove the associative property AH times BH times CH is equal to AB times HCH, that is equal to AB times CH, and that is equal to A times BC times H, that is equal to AH times BC times H, that is equal to AH times BH CH. So, we have proved that the associative property exists. Clearly, G bar H is a group, we have proved so. Next, we do one more theorem. Let G be a group and let Z of G be the center of G. If G bar Z of G is cyclic, then G is abelian. Proof: let G Z of G be a generator of the factor group G bar Z of G. Let A comma B belongs to G. So, clearly there will exist some elements I comma j such that A Z of G is equal to G Z of G the whole power I, because it is generator, that is equal to G power I Z of G. B Z of G is equal to G Z of G the whole power j, that is equal to G power j times Z of G. Therefore, A is equal to G I of x and x where x belongs to G, and B is equal to G j y where y belongs to Z of G. Then A B is equal to G I x times G power j y, that is equal to G I times x G j times y. So, we are clubbing these two elements together by removing the brackets, that is equal to G I times G j x times y. We are just reversing the elements here, and that is equal to G I times G j times x y. Now, all this is possible because Z of G is normal. So, G I G j x y. Our aim is to prove that G bar Z of G is an abelian group. So, which is why we started with AB, that is equal to G I of x times G I of y, and now we have come up to here, and therefore, that is equal to G I times G j times y x. We have changed the elements here. So, G j y times G j x. So, now we have proved that this is B and this is A. Therefore, AB is equal to BA. So, we have proved that this group is abelian. Next, we shall see one theorem, Lagrange's theorem, an important theorem. If G is a finite group and H is a subgroup of G, then the order of H divides the order of G and the number of left cosets of H in G equals cardinality of G divided by cardinality of H, or in other terms order of G divided by order of H. So, proof: let the order of H be equal to n and let the number of cosets of H in G be k. The set of left cosets of H in G partition G. Therefore, when we define a function phi, it is from the set H to GH and it is defined by the element H going to GH. So, we now show that phi is onto, it is clearly surjective. Also, to prove the 1-1 property, GH1 is equal to GH2. So, when you do left cancellation, it becomes H1 is equal to H2 and this proves that phi is injective. So, H and GH have the same order. So, order of GH is equal to order of H, which is equal to n. Now, G can be partitioned into k disjoint subsets with cardinality n, that is the order of G is equal to kn. Therefore, from here k is equal to order of G divided by n, that is equal to order of G divided by order of H, since n is equal to order of H. Therefore, we have now proved the statement of Lagrange's theorem. This is an important note that the converse of the Lagrange theorem is not true. That is, I am reversing the statement, if n divides order of G, there does not always exist a group of order n. For example, let us consider the alternating group A4 with order 12. It has no subgroups of order 6, but 6 divides order of A4. So, the converse is not true. Let us go to the next theorem. The quotient group of a cyclic group is cyclic. Proof: let H be a subgroup of G and XH is an element of G bar H. We now have to prove that G bar H is cyclic. Now, since G is cyclic, G is generated by a set of elements, namely G, and X is equal to G bar K for some K, which implies that the element XH, which is from G bar H, is equal to G to the power K times H, that is equal to GH the whole power K. So, clearly G bar H is cyclic. We have now proved the statement of this theorem. We shall see the first isomorphism theorem. Let phi be a group homomorphism from G to G bar. Then xi, a function defined from G bar kernel phi to phi of G, such that G kernel phi is going to the element phi of G. So, this particular function is defined like G kernel phi is going to phi of G, an element of phi of G. We have to show that this function xi is a isomorphism and this particular set G bar kernel phi is isomorphic to phi of G. Proof: first we have to show that it is well defined. Clearly xi is well defined because the elements are going to be equally mapped. To prove that 1-1 property exists, for that let us take phi of A is equal to phi of B. That implies and is re-implied by A kernel phi is equal to B kernel phi. Therefore, xi of x kernel phi times y kernel phi is equal to xi of xy kernel phi, which is equal to phi of xy. Let us see the elements here and here. That is equal to phi of xy, that is equal to phi of x times phi of y. Since phi is a group homomorphism, this property is possible, and phi of x is actually xi of x kernel phi and phi of y is xi of y kernel phi. So, we have proved that 1-1 property exists. So, we started from xi of AB to xi of A times xi of B, like that we have proved. So, the 1-1 property is existing and it is surjective, it is well defined. So, clearly it is a isomorphism since homomorphism property is also existent earlier. So, we have proved the first isomorphism theorem. Let us now show an example. Let phi be a function from the set of all permutation group. The permutation group is Sn. It goes from Sn to Z by 2Z. So, now phi of sigma, sigma is the permutation here. So, phi of sigma is equal to 1 if sigma is odd and it is equal to 0 if sigma is even. So, this is the function that we have defined. Clearly, phi is a surjective homomorphism and kernel phi is the alternating group An. So, Sn by An is isomorphic to Z by 2Z and we know that the cardinality of An is n by 2. Now, we shall see the second isomorphism theorem. Let G be a group, A and B be subgroups of G, and let us assume that A is a subset of Ng of B, where Ng of B is a normalizing subgroup of B. then AB is a subgroup of G and B is a normal subgroup of AB, A intersection B is a normal subgroup of A, and AB by B is isomorphic to A by A intersection B. So, we have to prove these statements. The proof: AB is a subgroup of G. Now, see, since A is a subset of Ng of B, where Ng of B represents the normalizing subgroup of B and B is a subset of Ng of B, clearly AB is also a subset of Ng of B. That is, B is a normal subgroup of the subgroup AB. Since B is normal in AB, AB by B is well defined. Now, let us define the function phi from A to AB by B by phi of A is equal to the element A times the set B. Therefore, AB by B is well defined and phi is a homomorphism. This can be verified. So, phi of A1 A2 is equal to A1 A2 B. This is the definition. So, phi of A1 A2 will be, instead of AB we have A1 A2 here. So, A1 B times A2 B, this is a small manipulation. So, phi of A1 times phi of A2. So, clearly phi is a homomorphism. Now, let pi be a function from AB to AB by B, and this is a natural projection homomorphism. Now, phi is a restriction to the subgroup A. So, this is a natural projection and phi is a restriction to the subgroup A. So, clearly phi is surjective. The identity element in AB by B is the coset 1B. So, kernel phi consists of A belongs to B, that is kernel phi is equal to A intersection B. So, this we are picking all the elements that belong to both A and B. Therefore, kernel phi will be A intersection B. Now, by the first homomorphism theorem, A intersection B is a normal subgroup of A and A by A intersection B is isomorphic to AB by B, hence proved. Now, we shall see the third isomorphism theorem. Let G be a group and let H and K be normal subgroups with H being a subset of K, and then K by H is a normal subgroup of G by H, and G by H by K by H is isomorphic to G by K. We have to prove this. So, the proof goes like this. Clearly, K by H is a normal subgroup of G by H. Let us define a phi function from G by H to G by K as G H going to G K. So, this is the mapping. So, we have to prove phi is well defined. So, for that G1 H is equal to G2 H, let us assume so, and clearly G1 is equal to G2 H for some H belongs to H, because H is a normal subgroup of K and H belongs to K, which implies that G1 K is equal to G2 K, that is phi of G1 H is equal to phi of G2 H. So, phi is well defined. Since G belonging to G is arbitrary, phi is a surjective homomorphism. Kernel phi is a set of all GH belonging to G bar H such that phi of GH is equal to 1K. So, 1K being the identity element here. Therefore, GH belonging to G bar H such that GK is equal to 1K, that is equal to the set of all GH belonging to G bar H such that G belongs to K. Since GK equal to K implies G belongs to K, and this is nothing but, when you look at the structure, it is K bar H. By the first isomorphism theorem, we apply this to our statement here. So, it is G bar H by K bar H is isomorphic to G by K. Now, let us go to the next theorem. For any group G, G by Z of G is isomorphic to in of G. In of G represents the inner automorphism group of G. Now, the proof goes like this. Let T be a function from G by Z of G going to the inner automorphism group of G, given by T from G Z of G to phi G being an automorphism here. Now, phi G of x is written as Gx G inverse for all x belonging to G. We have to prove T is well defined. Therefore, to do this, let us assume that G Z of G is equal to H Z of G, which implies H inverse of G. So, H is going here. For H inverse of G belonging to is now belonging to Z of G. Now, for all x belonging to G, H inverse of Gx is equal to x H inverse G. Thus, Gx G inverse is equal to Hx H inverse for all x belonging to G. So, this implies that phi G is equal to phi H. If we are going from the reverse, if phi G is equal to phi H, when we are retracing the argument, we can prove that T is 1 1. Similarly, we can show that T is onto. There are no remaining elements here, therefore, T is onto. Since phi G phi H is equal to phi G H for all G comma H belonging to G, T is operation preserving. So, from this all we can show that G by Z of G is isomorphic to inner automorphism of G. So, we have showed that it is well defined, the homomorphism property exists, we have shown that it is 1 1, we have shown that it is onto, and therefore, this is true, hence proved. Now, we shall see a definition. Let G be a group and let H be a subgroup. H is a characteristic subgroup of G if for every automorphism phi of G, phi of H is equal to H. We shall see a theorem now. Let G be a group and let H be a commutator subgroup, then H is characteristically normal in G. The definition of characteristic is here. So, subgroup is characteristic subgroup if the automorphism is phi of H is equal to H. So, characteristically normal. Now, the proof is, suppose phi is an automorphism of G and let x comma y belonging to G, then phi of x inverse y inverse x y is equal to phi x inverse phi y inverse phi x phi y. Let us recall that this is the commutator of phi x phi y. Now, therefore, phi of H is generated by commutators, and so phi of H is equal to H. So, from this definition we can say that H is characteristically normal in G. Let AH and BH be two left cosets, then BH, AH is equal to BAH when you are doing the product, and therefore, BA, this element is actually the commutator element, therefore, A inverse B inverse AB times H, that is equal to ABH. When you cancel the terms and you club them together, you are going to get ABH, and that can be written as AH times BH, which implies that G by H is abelian. So, I have proved that this element times this element is equal to the product of the reverse also. So, it is abelian. So, now let us consider a function phi from G to G dash to be a homomorphism. Let G dash be abelian. Now, to prove that kernel phi contains H, suppose x comma y belongs to G, then phi x phi y is equal to phi y phi x, that is, which implies phi x inverse phi y inverse phi x phi y is the identity element in G dash. That is, x inverse y inverse x y is mapped to the identity. Since phi is mapping from G to G dash, we say that this element is mapped onto the identity. So, commutator of x and y lies in the kernel of phi. So, we have proved the theorem statement. The next theorem, let G be a finite group with a normal subgroup n such that the GCD of the order of n and the order of G by n is equal to 1, that is, they are relatively prime. Then n is a unique subgroup of order of n. The proof, let G be a finite group and let K be a subset of G such that order of K is equal to order of n. Then Kn by n is also a subset of G by n. So, from this, order of Kn by n is equal to order of Kn by order of n, that is equal to order of K by order of K intersection n. So, from here we arrive at this result. By Lagrange's theorem, order of K by order of K intersection n divides order of G by n, but order of K is equal to order of n, and the GCD of order of n and the order of G by n is equal to 1. So, this implies that order of K by order of K intersection n is equal to 1, hence K is equal to K intersection n. So, this implies that K is equal to n, and therefore, we have proved that the statement n is a unique subgroup of order n. K and n both have order n. Let us see a definition now. A sequence G0, G1 so on up to Gr of subgroups of a group G is called a normal series of G if the identity element is equal to G0, a normal subgroup of G1, G1 is a normal subgroup of G2 and so on up to Gr, and all of this is equal to G. The factors of a normal series are the quotient groups Gi by Gi minus 1, where 1 less than or equal to I less than or equal to R. So, this is the normal series where one is nested within the other. The next definition, let G be a group, a normal subgroup n of G is called a maximal normal subgroup if number 1 n is not equal to G and H is a normal subgroup of G and H contains n, which implies that H is equal to n or H is equal to G. We shall now see a theorem. Let H and K be distinct normal subgroups of G, then H intersection K is a maximal normal subgroup of H and also of K. The proof goes like this. By second isomorphism theorem, H by H intersection K is isomorphic to hk by k. Now k is a normal subgroup of hk, which is also a normal subgroup of g. Now hk is equal to k or hk is equal to g. Since k is maximal, but hk is equal to k, which implies that h is a subset of k, which is a contradiction. Since h and k are maximal and distinct, hk is equal to g. This implies that h by h intersection k is isomorphic to g by k, which implies that h intersection k is a maximal normal subgroup of h since k is maximal. In this module, we saw about quotient groups, cosets and their various properties. We studied the Lagrange's theorem, the three isomorphism theorems. I hope this was useful to you. Thank you.